go one more time, finding probability that a sample statistic falls into a certain interval. So we've covered X bar and P hat, the sample mean and sample proportion. So in this video, I want to focus on the sample variance S squared, or equivalently the sample standard deviation S. When we did the distribution of S squared the first time, right, we covered the fact that S squared does not have a nice distribution by itself, but under the right conditions, it is directly related to a chi-squared distribution. And so sometimes we can transform our sample variance, or equivalently sample standard deviation, into a chi-squared distribution. The requirement to do this is that the population you're sampling from must be normal. Okay, so this is an absolute. So if your parent population is normally distributed, then we can transform S or S squared into a chi-squared score using n minus 1 times S squared over sigma squared. Let's look at a couple of examples. So one more time, we're going to take a look at the hill route and the time it takes to make a full loop. Okay, recall that the times are normally distributed with a mean of 24.4 minutes and a standard deviation of 3.9 minutes. And we want to know the probability that the variance in the amount of time it takes for 250 round trips to be made is more than 36 minutes. Okay, so we want the probability that the sample variance, S squared, is greater than 36. We need to know the distribution of S squared. Okay. And the population we are sampling from is normally distributed, right? Which means that our sample variance S squared is related to a chi-squared distribution, and we can transform, right, the S squared, the sample variance of 36, into a chi-squared score and use all the chi-squared distribution tools that we have to find this probability. To use our transformation, we have to make sure we have all our parts identified. N is our sample size, that's 250. Sigma squared is our true variance. We know the true standard deviation is 3.9, so we're going to need to square that to get the variance. And the value of S squared, that is our boundary, is 36. We want S squared to be 36 or higher. So I'm going to replace N with 250, sigma squared with 3.9 squared, and S squared with 36. Okay, so a sample variance of 36 equates to a chi-squared score of 589.349. Now, notice the degrees of freedom here. The degrees of freedom is the sample size minus 1, so we're going to have 249 degrees of freedom. Okay. So when we go to our graph, we have to know which side of the graph to shade. To determine which side of the graph we're going to shade, we need to take a closer look at the relationship between the sample variance, right, S squared, and the chi-squared score. Currently, we had S squared of 36 as our boundary, and when our sample variance S squared was 36, our chi-squared score was 589.349. We're interested in the probability that we get a sample variance of 36 or higher. So we need to take a look and see what happens if we had a higher value for S squared. Okay, so how would the chi-squared score change if we had a higher sample variance? Suppose we had a sample variance of 40 or 45 or 50. Okay, what would happen to the corresponding chi-squared scores? So in each case, as S squared got larger, 40, 45, and 50, you can see that the chi-squared scores keep getting larger and larger. So we want the probability that S squared is greater than 36, which means we want the probability that the chi-squared score is equivalently greater than 589.349. So we're going to shade everything to the right. What we've done is turned the original question about the probability that S squared, the sample variance, is bigger than 36, into a question about the probability that a chi-squared score does something. and we know how to handle probability when we have a chi-square distribution. We're going to need to draw our chi-square graph. 249 degrees of freedom, that's our sample size minus 1. Okay, so the mean is 249, because on a chi-squared, the mean is always equal to the degrees of freedom. So 589 is way over here on the right-hand side, and we want the probability of getting that chi-squared score or a higher one. So you can barely see this little tiny piece of shading in blue on the right-hand side of the graph. And we want to find that probability using our chi-squared CDF. Okay, so we're going to use our chi-squared CDF from that point to infinity. And you'll see here, I've gone back to the original transformation. Right? This is going to be a little bit more accurate than if we had rounded that to the 589.349. Now, in this particular case, we're getting 1.235 e to the negative 29th, or in other words, 1.235 times 10 to the negative 29th. Okay, so that's going to have the effect of moving the decimal place 29 places to the left. So we're talking about 0.0028 zeros later, 1235. So obviously in this case, if we had rounded that chi-square score a little tiny bit, it wouldn't change our understanding of the situation in this case. But there are times when it would. So as often as possible, use exact values in the intermediate steps. Okay, so I know this looks like the exact same question, but there's a slight difference. You're still talking about the hill route and the amount of time it takes to go through a full loop, and we want probably the standard deviation. So we've gone from variance to standard deviation. We want probably the standard deviation in the amount of time it takes the 250 round trips to be made. All right. We want to know probably that the standard deviation will be more than 6 minutes. So the standard deviation is S. So we want the probability that S is greater than 6. So we already know that this distribution is normal, therefore S and S squared, right, are both directly related to a chi-square distribution. So we can transform our value into a chi-square score. So this time, 6 is a sample standard deviation. So when I plug it into the equation, I have to plug it in for S, which means I need to square it because the equation has S squared in it. Okay. Which, once we square the 6, we're back to the 36 variance. So this is the exact same problem we just did, only worded in terms of the standard deviation. Okay, which means when we did our conversion, we had to square S, where last time we already had S squared. So either way, we get the same chi-squared score, which means we're going to get the same graph and the same probability. Okay, so any question about the variance can be written as a question about the standard deviation and vice versa. We just have to be careful about which one we're starting with and use our equation appropriately, making sure that if we have S, then we plug in S. If we have S squared, we're plugging in for the entire S squared. Let's look at a couple more examples. Okay, so we're rolling the fair 6-sided die 200 times. Again, we've talked about this several times before. This time, we want to know the probability the variance will be less than 2.2. So we want probably that the variance S squared is less than 2.2. Okay, so when we roll the die, the outcomes are going to be either 1, 2, 3, 4, 5, or 6. Okay, so that is definitely not normal because it's a discrete population. And normal distributions, among other things, and first and foremost, are continuous, not discrete. And because this population we're sampling from is not normal, the chi-square distribution transformation can't be used. We don't know the behavior of S squared, or at least it's not nice enough to worry about in this class. And so because of that, we can't find this probability. And that just happens sometimes with the tools we have. Here we go back to the UC to get some food. And this time we want to know the probability that the standard deviation in wait times for our 15 randomly selected patrons is less than 10 minutes. Okay, so standard deviation being either S or sigma. It's for a sample of 15 randomly selected customers, so that is going to be S. So we want the probability that S is less than 10. Now, the population we're sampling from, we're told, is skewed left, okay, which is not normal. Right? The normal distribution is perfectly symmetric. And because the population we're sampling from is not normal, we cannot relate the sample standard deviation here to a chi-squared score. So we can't do our chi-squared transformation, which means we also can't do this probability. For this last example, we're going to go back to talking about how many people paint the rock each year. So we want to know what the probability is that the standard deviation in the number of people that took part in painting the rock is more than 50 for the 5 random years we selected. So those 5 years are a sample, which means we want the probability that S is more than 50. To do this, we need to know the distribution of S. Okay, so the population we are sampling from is normally distributed, which means that S and S squared can be transformed into a chi-squared distribution. Okay, so we're in a situation where the distribution of S squared is going to be manageable. Now that we've established that the sample standard deviation can be converted into a chi-squared score, we're going to go ahead and do that. So 50 is the borderline value of S we care about, so we need to transform that. So I'm going to plug 50 in for S. Again, our sample size was 5. And sigma, the standard deviation of the population we're sampling from, was 47. So sigma squared will be 47 squared. And so when we crunch those numbers, we end up with a chi-squared score of approximately 4.527. Like we discussed before, we want to probably getting this value of S, 50, or a larger value. So if we replace the 50 with a larger value like 60, 70, 80, that would cause this chi-squared score to go up. So we want to probably getting this value for the chi-squared score, 4.527 or higher. So when I draw my graph, I'm going to draw a chi-squared graph, 4 degrees of freedom. Again, that's the sample size minus 1. And we're going to shade everything to the right of the 4.527 because 4.527 equates to or represents the S equaling 50. And we want S to be 50 or higher. So we want our chi-squared score to be 4.527 or higher. And now we're going to use the chi-squared CDF. And I want to show you here, if I round that chi-squared score to 4.527, we get this probability. And if we use the exact transformation without any rounding, we get a slightly different probability. Now, again, in this case, you notice if we round this out to 3, 4 decimal places, we're okay. But the 5th decimal place, when we start rounding there, now we're getting slight differences. So you want to be careful, again, when you're using an online homework system, to make sure that we're as accurate as possible for as long as possible. If you have any questions about the topics covered in this video, or anything else that's happening in your statistical reasoning class, talk to your instructor, go to their office hours, or take advantage of the free tutoring available in the Math Tutorial Center. Good luck, and go Vols!